Okay, so welcome everybody to this new lecture of the Th-LYR event. I am Claudio Bonanno, and today is a pleasure for me to have Davide Vadacchino as a lecturer today. Davide is currently a postdoc at Trinity College in Dublin, but he has also been a postdoc in Pisa and in Swansea, and is going to talk about lattice field theory and in particular of lattice QCD. So before starting, I just want to say that please feel free to ask questions at any time. So just unmute yourself and ask the question. If you prefer, you can write in the chat and I can read, or Davide can read the question. So please don't be shy, because the idea of these lectures is to make them interactive. Okay, so Davide, please.
Okay, thank you, Claudio, for the nice presentation, and thank you to the organizing committee for organizing these lectures. As Claudio was saying, I have prepared these lectures with, let's say, a path in mind. So a path that led to a better understanding of what will be the subject of this lecture. So, and questions are obviously a paramount part of the understanding. So again, let me repeat what Claudio said. Please feel free to interrupt me and to ask questions at any time. Now, as the title says, these lectures will be on lattice field theory, a primer of methods and results. They will span over 2 lectures. In the first lecture, I will try to give a theoretical background of the lattice regularization in quantum field theory in general. I will try to, let's say, to explain the conceptual points in the many discretization that one has to face when regularizing on the lattice a quantum field theory. I won't perform all the calculation, but I will perform those calculations that I deemed interesting, and I will refer to textbooks, for example, the ones that you see here, textbooks on lattice field theory, that contain many more information and derivations than the one I can perform today, and also to books on quantum field theory. I bet that the 2 on quantum field theory, you know them already. So in particular, I will refer to volume 1 of Weinberg and to this book of Whiteman and Strater that's called CPT Spin Statistics and all that. And occasionally, I will also refer to research papers. Very well. In the second lecture, I will try to explain the practicalities and also the theoretical underpinnings of the Monte Carlo methods that are today an essential tool in the study of these lattice regularized quantum field theories. Very well. So I think that the introduction is enough. So let me start without much further ado. So we will start. Sorry, here I must understand, okay, how to put a new slide. Sorry. Okay, very well. So I will start with a very generic introduction to quantum field theory. I bet that the majority of you is very familiar with this, so I won't take much. So when we deal with a quantum field theory, we deal with a set of ingredients. And these have been studied very thoroughly in mathematics. And people have come to a set of axioms that can describe the great majority of the simplest quantum field theories. As you well know, there is a 1 million prize for whoever is able to demonstrate that Yang-Mills theories have a mass gap. So we are not to the point where the whole quantum field theory is explained and in a rigorous way mathematically, but there is nevertheless a sound basis of arguments. So obviously the first ingredient is a Hilbert space of states that I will denote with this H. Now this state will contain all the states of your theory, so the one particle, two particle, n particle states, and also the bound states, etc. Everything that should appear in the theory. Then we have a unitary, and let me stress, unitary representation of Poincare group. Now this unitary representation of Poincare group will map the Poincare transformation to matrices in complex space. And we require, first of all, that the translations are represented in this way, where this dot here is really a Lorentz product, and this is P, the generator of translations. And we require in particular that the spectrum of P lies in the forward light cone. Also, we require that there is a state in the Hilbert space, and this state is the only state that is invariant under the action of the representation of Poincare group. Then obviously, in our theory, we will have fields. Now we will indicate generically with phi computed in X, where X is a point of space-time, and these will be operator valued distribution. So we have a complication here. As you well know, it makes no sense to think of the field at a point. It is a dynamical variable, but whenever you do calculations, unless you want divergences to appear everywhere, you have to smear the fields over a neighborhood of space-time. And the properties of these fields is that they should transform covariantly under the representation of Poincare group, and that obviously there is a causality condition. So two fields computed at space-time points that are separated by a space-like interval will commute, and this is quite intuitive. So now, if we have a theory that satisfies these assumptions, then there is a very important theorem, and I will state it heuristically, but you can find the proof in the book by Strater and Whiteman, CPT, spin statistics, and all that. And the theorem basically says that if you are able to compute these objects that are the vacuum expectation value of the fields computed at points x1 to xn in space-time, then you can reconstruct the Hilbert space. Now, these objects are very complicated objects. They are operator valued distributions again, and they are intended to be smeared with functions that go to 0 at infinity more than any power. But nevertheless, there is a famous representation that, again, you are all familiar with, by path integrals. So what we have here is that the Whiteman function can be formally represented as a product from 1 to n of functional derivatives with respect to a source jxi of a generating function, and when the computation is done, you just put the sources to 0 and you get your amplitude. Now this zj, that is the central object here, will be represented, sorry, let me write it correctly, okay. Will be represented as a functional integral over phi of exponential of I over h bar, the action, the classical action, plus I times the integral over Minkowski spacetime of jx phi X. Now, an example of the reconstruction theorem you can find, for example, with the knowledge of the Cullen-Lehmann representation in the two-point function. Now, it is an easy exercise that you find in textbooks, for example, QFT volume 1 of Weinberg, to see that from the knowledge of the two-point function, you can reconstruct the one-particle spectrum. And this is the prototype of things that we do on the lattice, basically. We use non-perturbative analytical argument. We compare with non-perturbative findings on the lattice, and then we extract the physical information. Now, this representation is formally very useful because it allows you to compute virtually any function. However, it is plagued with problems. And the first problem is that when we write the functional measure of this object, implicitly there is a limit inside this object, and moreover, it is very hard to characterize topologically this complex oscillating phase factor. So this has to be taken with care, and it can only be written down in particular cases. So this needs to be defined. Then we have the problem that it may happen that we are interested in a regime of the theory where the coupling is strong, for example, or we can be interested in configurations of the field around which to perturb the field that are not immediately easily includable in perturbation theory. So we need a way to capture the interesting physics. So we need something that goes beyond perturbation theory. So it might not capture the interesting physics. And then, as you all know, this is a formal writing, but in reality, we have first to take the infinite volume limit, and then to take, and this is the first appearance of a momentum cutoff, we have to take the limit where the cutoff is sent to infinity, and the UV cutoff, the UV minimal distance is taken to 0. And now this will give rise to divergences. Now let me give you the good news. So the lattice regularization solves all this. We will be able to define rigorously this integration measure. We will be able to see how we can capture the non-perturbative physics, and also the divergences will be eased. Very well. So let me add another important step to this construction. Again, I think that you are all familiar with this. So this is another essential step in the lattice regularization of quantum field theory. One starts with the path integral regularization, the path integral representation, and then does a Wick rotation. So under the assumptions that I presented above, the assumption of Whiteman and Streeter, it is possible to define a Euclidean Green function now this is equal simply to the Whiteman function above, but computed in Euclidean time. So let me just say 2 words about that. So initially, if you take the Whiteman function, it will be the difference, a function of the difference between coordinates, and in particular of the time coordinates. And it is easy to see that under the assumption that I have made at the beginning, this you can write as an expectation value of fields. And then for each pair of fields, you can insert time. time translation, actually space-time translation. And you see that under the condition that the spectrum of this operator is contained in the forward light cone, you get a function that is analytical in the lower complex plane. Now you also get that for space-like separated argument, you have a function that is well defined also in this area of the complex plane. Here you will have cuts. And so you will be, the result will depend on how you approach the cut. And then you will also have the property that for space-like separated arguments, the fields commute. So actually, you will be able to continue the function to the positive complex plane. So in the end, you will have a function that is defined on the whole complex plane. Now, what is interesting, except the cuts, obviously. Now, what will be interesting to us is this part of the complex plane. Here, Euclidean green functions will be defined. So we will work with Euclidean green functions because they are much easier to manipulate. So for example, note that all the arguments here can be interchanged because the separation between points in the Euclidean space is space-like. So these will be symmetric. And but obviously, and we will be able to perform many manipulations as if we were treating analytical functions instead of operator value distributions that are very complicated objects. Now, in the end, we will need to go back to Minkowski space. And the conditions under which this is possible are called positivity conditions. And again, these you can find in the book by Osterwalder and Schrader, by Streeter and Whiteman, but also in a research article that is Axioms for Euclidean green functions by Osterwalder and Schrader. Very well. So, but the most important result is that now you also have a path integral representation. I will denote initially these Euclidean space-time points by a superscript E. And so I will do for the generating function. And now you see that by performing a weak rotation, you have a nice decaying exponential. And so you are happy because there is no oscillation anymore. And your integration measure is a well-defined object. Very well. So I bet all this is familiar to you. Let me just state two properties of Euclidean path integrals, and then I will go on to define the discretization on the lattice. So first property, so let me just write this here. First property, you immediately see that this object looks like a partition function of classical statistical mechanics. And this will be very important because this tells us that we can simulate this system on a computer exactly as we do for system of statistical mechanics with Monte Carlo methods. And the Monte Carlo methods will be the subject of the next lecture. And other important feature, if you write down the partition function of this quantum system at finite temperature, then you can find through the explicitation of the trace a representation in terms of path integrals. So this integral over Euclidean time denoted by x4, and then the integral over Euclidean space of the Lagrangian density Euclidean Lagrangian density, LE. Now, the difference here is that the field will have to be, will have to have specified boundary conditions, and in particular, plus for bosonic fields, minus for fermionic fields. Now, with these two instruments, we will be able to run Monte Carlo simulations of lattice quantum field theory at finite temperature. Very well. So now, without nothing much, I can pass on to define the lattice. Now, I will start with the definition of the main tools that one uses in discretizing theories on the lattice. And then I will try to discretize the most common actions, so the free scalar field, the fermion fields, and the gauge fields. And in passing, I will try to point to some of the most important conceptual problems. As I said before, I won't perform all the calculation. I will perform some of the calculations that bear similarities to all the most complicated cases so that you can orient yourselves. And then I will point to textbooks so that if you are interested, you will be able to find everything in the references. So here we deal with a lattice. Now, what kind of lattice? I will deal with an hypercubic lattice that I defined as lambda, and this mathematically will be defined as n mu a, where n mu belongs, each n for each value of mu belongs to the integers, and mu has 4 values. A is the lattice spacing of my lattice. Let me note two things. First, I have chosen a hypercubic lattice, but actually I can choose any lattice. And as long as I flow correctly to the continuum limit from the theory of the renormalization group, you know that I will explain later. You know that let's say the microscopic features of the system will be unimportant because the correlation length, that is the only scale in the system, will go to infinity. Another notation here is that I have limited the number of dimensions to 4, but actually this procedure could also go on and I could work in more than 4 dimensions. So now the most straightforward path is to simply discretize all the objects that we deal with currently commonly in quantum field theory. So for example, the integral over Euclidean spacetime becomes a to the 4th times the sum over the sides of the lattice. And to make an example, if I have two functions, f and g, whose scalar product is defined on Euclidean space like that, to real functions, so that I don't have the complex conjugate, then this will tend simply to a to the 4th sum over the sides of the lattice, f computed in site n and g computed in a site n. So this is, as you see, this is quite straightforward. This notation is useful because, as you will see, when we deal with Euclidean actions, there will be integrals, and so it is better to have a Swift notation. So this is property 2. Then property 3, if you have a Euclidean derivative along direction mu, well, this time the choice is not, there is not only one choice. You have the forward derivative that I denote with a plus, and with a function, acting on a function, this is 1 over a times f computed in n plus a mu. So let me stop one moment. When I say n, I say a side of the lattice. When I say n plus a mu, I say a neighboring side in direction mu. But I could also have another neighboring side at direction mu. Okay? So this is basic minus fn, and this is basically the ratio that you take when you compute derivatives, except that now the number a is not taken in the limit of a equal to 0. But we also will have the backwards derivative, and in this case, the expression will be 1 over a times f of n minus f of n minus a mu. So each of these are characterized by a direction. It is the directional derivative, basically, and a plus or a minus. Now, I also have other definitions, and in particular the symmetric derivative, but we will see in one of the later treatments how this is used. Here I want to state a very useful property, and I will leave the demonstration of this property as an exercise to the reader, like in textbooks. And I assure you that the demonstration is not hard, it is possible. So if you have the product of these two objects, I suppressed the mu to make it simpler, then you can show that this is equal under the assumption that the functions go to 0 at infinity, or under periodical boundary condition, you have this property. So the operator lambda plus in one of member of the scalar product goes to the other member and becomes lambda minus with the addition of a minus. And this will be useful in the following. Now, another property is the Fourier transform. The Fourier transform in the continuum is denoted like that. And I put a tilde on the Fourier transform, and this on the lattice becomes the following. Note that I am integrating over the first Brillouin zone, because the functions will not be able to have a wavelength that is less than the inverse lattice spacing. So let me state first Brillouin zone, and I will also have the property that the Fourier transform will be a periodic function. Very well. Now, if I want to invert this Fourier transform, I will just have to perform the same calculation as in the continuum. Okay, now the last property, that is one of the most important ones. Now the integration function, the integration measure will become a simple integral over the sides of the lattice. So the path integrations that we have seen until now will become simple multidimensional integrals. So there will be no need to do complicated journeys into very complicated mathematics, and it will be very straightforward, and obviously it will allow us to put the system on a computer and to extract physics from there. So let me just state that this exercise you find in the book by Rocco. Very well. Now I urge you to go have a look at that book. It is very, very nicely written. But now let me just pass on to the case of the free scalar field. Very well. So a calculation that is nice to do and is full of knowledge is the calculation of the Euclidean action of the scalar field. So there you see the difference between doing a change of variables in an integral and doing an actual weak rotation. So I urge you to do the calculation. And I will write the action in this way, and m naught will be the bare mass. I will denote, I will call it bare mass, even though we don't have an interaction, because then I will generalize some of the things that I will say. So we start with this Euclidean action, and we discretize it by applying the rules that I stated 5 minutes ago. So we will have a lattice version of this, this action. So I will have a sum over the direction of the product of the forward derivatives of the fields times 1/2 times m naught squared times, again, the scalar product of the field. So in here, you don't see a sum over the sides anymore because it is hidden into this notation. Note that in the first term, I could have chosen lambda minus, so the backwards derivative, but since this is parity invariant, there is no difference really. So you can choose both. Now, a very important step in this derivation is to remember that the property that I asked you to demonstrate as an exercise okay, so now let's write explicitly these operators acting on a field. Now this will be lambda minus, then 1 over a coming from the first derivative, then phi computed in a plus mu minus phi computed in n, and then we can explicitate the lambda minus, and we will have another 1 over a, so this will result in an 1 over a squared, and then phi in n plus a mu minus phi over n. So I'm letting the backwards derivative act on the first term in the parentheses, and then I will let it act on the second term. And this will have phi computed in n plus this time, and this plus is very important, plus phi computed in n minus a mu. So this will be 1 over a squared phi of n plus a mu plus phi of n minus a mu minus 2 phi n. So if I plug this back into the Euclidean lattice action, I see that, and I explicitate the sum over the sides of the lattice, I see that an a to the fourth will appear, a sum over the lattice sides will appear, and then a sum over the directions that comes from here, and then I will have minus 1 over 2 a squared. The 1 over 2 comes from here, and the 1 over a squared comes from here, and then I will have this expression. So I will have phi to the n plus a mu plus phi to the n minus a mu times phi of n, and then I take this term and I regroup it with the mass term, and the result will be 1/2 of 8 over a squared plus a naught squared phi squared of n. Note that there is an 8 here. The reason for this 8 is simply that I have summed over the direction, and in the sum there was also this term phi n, and when you sum over the direction something that doesn't depend on the direction, you simply get the factor that is the number of elements in the sum. So at 8 times 2 will give 4 times 2 will give 8. Very well. So let me just factor the a squared that is in the sum, and this will become a minus sum over mu of phi n plus a. Note that I interchanged the place of the phi's, but this is no importance because we are dealing with classical quantities, plus 1/2. No, here there is a little mistake. So yeah, 8 plus m naught squared a squared times phi squared n. Now, why did I write the action in this way? There is a reason. The reason is that since we know that the Euclidean action has the same units as h bar, and in natural units this is 1, so it is dimensionless, then we see that we can express the fields and the masses through dimensionless objects. So if you remember the dimension of a scalar field, you immediately realize that it is in length unit, it is 1 over length, and the mass is also 1 over length, and you can write it in this way, where the phi hat and the m hat are dimensionless. And this is very nice, because then the lattice action will become a sum over pairs of points on the lattice times phi dimensionless computed in n times a kernel k times phi computed in m. Watch out, because m is not the mass. I always write the mass with a subscript, where this object is simply the sum over the directions of delta n plus a mu plus delta of n minus a mu m, and then 8 plus m naught hat squared times delta m n. So I wrote this in this way because now it is apparent that the integration, the generating function is a finite multidimensional integral over phi hat times the exponential of minus 1/2 sum over pairs of points on the lattice k n m times phi m. And this is a simple Gaussian integral. So it is proportional to 1 over determinant of the 1 over square root of the determinant of the kernel. So you can perform the calculation explicitly, obviously not analytically, but actually you can do it analytically. But most importantly, you will be able to do that on a computer. Now, this also tells us that once we have solved the free theory, we can use the Wick's theorem, both to do calculations in the free theory, but most importantly, we can use it to do any calculation in perturbation theory, as long as we can do perturbation theory. And this, the fields without the hats will be equal to 1 over a squared. The fields with the hats, and this, you can do the calculation, it is the inverse of the kernel. This is a finite matrix, and so you can compute it, and we will compute it, and the net result is that from the Cullen-Lehmann representation, you can get the one particle spectrum. And this is a calculation that we won't do, but I will tell you how to do it. And it will have a certain importance in the following. Very well, so let us do part of the calculation of the inverse of this operator. So we have the product between kmn and k to the minus ml, and this, if k to the minus 1 is the inverse, should be delta of nl. Now we pass to Fourier space. So remember that the integral is done on the first Brillouin zone. This time it will be on a 4-dimensional Brillouin zone. And then we will have this object. And the object that we are after, I will call it G, tilde, because it is in Fourier space. And I will also put a hat. And sorry for the over notation, but this is important because this will be the dimensionless propagator. And then we will use the fact that the delta as a representation in Fourier space, that is the usual representation, as follows. Again, with the integrals going from minus pi over a to pi over a. Now, if we rewrite this object in Fourier space, we can let the sum outside, we can interchange the sum and the integrals, and what we get is the integral from pi over a to pi, from minus pi over a to pi over a of k, then the sum over m of k and m acting on the exponential. And then we have our dimensionless propagator. And on the other side, we have the representation of the delta. Now, I bet you are familiar with this kind of calculations. Here I have, sorry, n. You are familiar with this kind of calculation, and you know that you just have to compute this object. And this object, I will fast track. You can really, it is a simple calculation. Sorry, there is a sum on m. It is a simple calculation, and it turns out that this is e to the I k n minus L times a. And then you just have to apply the delta functions to the exponential. And what you find is minus sum over the directions, e to the I k a mu. But now this k a mu is simply the component of k along mu. So I will denote it by a k mu a plus e to the minus I k mu a. Then minus 2 coming from one of the terms of the Euclidean action, and then plus m hat naught squared. Now this exponential is the same as this exponential. So the result, the net result of this calculation is that the dimensionless propagator in Fourier space will be equal to 4 sum over the directions. Actually, let me do one step less. 2 sum over the directions, 1 minus the cosine of k mu a plus m naught hat squared. And this becomes the cosine. So it is a simple manipulation. But now this is not the most comfortable form for this. Sorry, I have forgot the power minus 1. But this is not the most comfortable form. The most comfortable form is using the properties of trigonometric functions to write the square of the cosine in this way. And from here, you see a very important property. The object that we have in the denominator is strictly positive. So it will be obviously if m naught is not vanishing, but this will be important. And also this manipulation will be important when we come to fermion fields. Now, this is related to the dimension full propagator as follows. Okay, so what do we do with this propagator? Well, as I said before, once we have the propagator, we can use the properties of the non-perturbative analysis of quantum field theory, namely the Cullen-Lemma representation. So in principle, once we have this, we are able to compute the Fourier transform, the inverse Fourier transform in time, and work out the one-particle spectrum. Now, in this case, it is trivial, but in the interacting case, it may not be. For now, let me just note that if I just take the naive continuum limit, and the reason why I call it naive will be explained shortly. If I take the naive continuum limit of the real propagator, so the dimensionful propagator, I will have this limit. So a squared here, and I separate the sum k4 over 2 plus sum over I sine squared ki a over 2 plus m naught hat squared. And then you see from here and from the property of limits, so it is really trivial, but I nevertheless, let me do it. I can get k squared. Sorry, here I have a square. Sorry. Here, like that. And then sine squared k mu a halves. And then I see that these objects tend to k squared when a goes to 0. The morale of this step is that the limit, the naive continuum limit of j tilde k is exactly the Euclidean propagator of the continuum theory. Note that there is an a squared here and an m naught hat down here. So we recover also the fact that m naught is m naught hat over a. As I said before, you can also work out you can do the same calculation basically in the interacting case. And in the interacting case, m naught will not be the pole, but the pole will be displaced. But nevertheless, by using complex integration in the following way, you will be able to work out. So this is an integral over k4. You will be able to work out the time dependence of the mixed propagator, and these at large distances, sorry, at large Euclidean times, will be the energy, and the lower energy will dominate, and you will be able to work out the mass of the one particle state. And this is an exercise that I urge you to do. It is a simple integration in complex space, and you can also find it in the book by Ian Smith. Now, I stated just a few minutes ago that I am talking about the naive continuum limit. Now, let me be more definite about what I intend with naive. And this is the first very fine conceptual point of this lecture, naive continuum limit. In the naive continuum limit, you just take A to 0, so the lattice spacing to 0, and you keep the bare quantities fixed. Now, why do I call it naive? I call it naive because generally your physical observables can be written, they have a dimension, and they can be written as something dimensionless times a power of their dimension, their length dimension. Now, these in general, this O hat will depend on the bare quantities. So if you keep the bare quantities fixed and you send A to 0, two results are possible: plus infinity if the O is less than 0, 0 if the O is greater than 0. So this is not very interesting, except in the cases in which there is no interaction, or in very simple theories, this is not of interest. What is of real interest is the proper continuum limit. In the proper continuum limit, again, we send A to 0, but this time we keep the physical quantities fixed. So let's do an example. In the free theory, if we compute the renormalized mass, we get something, and we can express it in a dimensionless quantity over A. And in this case, it will be m naught. Okay? But if we go to an interacting theory, in general, for example, the phi to the fourth theory, we will get that the renormalized mass again can be expressed as mr hat over A. But this time, this will be A to the -1 times a function of the bare parameters. Now, if we want mr to be constant as the cutoff goes to the lattice spacing goes to 0, then, and this is general, and then we need the dimensionless renormalized mass to go to 0 as n goes to 0, because otherwise we come back to the naive continuum limit. This is very important because you know that the renormalized mass, dimensionless renormalized mass, by using the map between quantum field theories and statistical mechanics, is just the inverse correlation length of the system. And then you see that setting MR at to 0 is equivalent to sending the correlation length to infinity. Now, this you can do by tuning the bare parameters of the system, exactly as you do in statistical mechanics. Think of the Ising model. You can tune the reduced coupling and the temperature, and at some point we will have a second order phase transition where the correlation length will go to infinity, obviously in an infinite system. We will say something later about finite size effects, but still, when the correlation length becomes larger than the system, it is effectively infinite. And at this point, very important, you have a second order phase transition. So basically, to take the proper continuum limit of a theory, you have to tune the bare parameters so that the statistical system is at a second order phase transition point. Two things to note. One is that a priori we don't know if there is a second order phase transition in the statistical system and where. And very important, a priori, we do not know to what system we flow. So it is possible that we have a discretization, and we will see an example with the Fermion field. It is possible that we have a discretization, a very simple discretization, and that we take the continuum limit. But already at the naive level, we see that the theory to which we flow in the continuum is not the theory that we had discretized. And this should be also familiar to those of you that have studied renormalization theory. Some discretization will break some symmetries, and it will not be possible to recover them when we renormalize. Now I'm using these two terms. I've used regularization and I've used renormalization. We will shortly see how to map these words to the lattice case. Let me just complete here. To what theory do we flow? And again, we do not know a priori. So we have to check that the theory to which we flow is in the naive continuum limit, the correct theory, and this will allow us to use the proper continuum limit. So we have two kinds of limit. This is good, and this is not so good. I mean, it can be useful, but it is not what is physically interesting. So now the question could be, how do we compute MR, for example? Now MR, we have two ways to compute it. Perturbation theory, for sure. You just take the 5 to the 4th theory, you compute MR at a certain power of the coupling constant, and then you can perform all the manipulation that you want. But there are cases in which this is not possible. For example, when you have a strongly coupled system, and then you must resort to a numerical calculation. This will be the subject of lecture 2. And in the case of numerical calculations, I anticipate to you that what you do is usually studying the 2 points correlation function in Euclidean time, and from the exponential decay, you find whatever you want, basically, especially the masses of states. Very well. Now let me just say another 2 words about the continuum limit. So what is the relationship with respect to the continuum? So the continuum renormalization theory. So in this case, in the case of the continuum, we can do regularization with a hard cutoff. And on the lattice, when we discretize, we are doing a discretization on a lattice of lattice spacing A. And this A is the inverse of the hard cutoff. Renormalizing is the same as taking the proper continuum limit. So basically what we do is that we take our system, we choose values of the bare coupling constant to be in the neighborhood of a second order phase transition. We measure the quantities on the lattice, we set them equal to the physical quantities, so the result will be dimensionless quantities, and then we change the bare coupling constant to flow towards the second order phase transition, and we see that our dimensionless, for example, the correlation rate will increase, and the lattice spacing, obviously, that can be computed as a ratio between the dimensionless constants, the dimensionless quantities and the lattice spacing will decrease. So if we have enough points of this kind, we will be able to reach a continuum limit. Now, let me note something. At this point, many of you will know many kinds of regularizations. For example, you can put a hard cutoff, but you can also put dim reg. So you can use dimensional regularization. The difference is which symmetry is broken. So in the case of the lattice regularization, so lattice field theory, you break at least Poincare symmetry, because you are discretizing. So for example, you don't have the rotational symmetry anymore. Now breaking, I say at least because, as I said before, in trying to discretize actions, it is possible that some further symmetries are broken. Now, let me state another important fact. As I said, usually you measure an observable on the lattice, and this will have some length dimension. And the dimensionless quantity will be a function of the bare quantities. Now, this is telling you that you can invert the dependence and express A as a function of the physical quantity of the bare and of the bare quantities. And this is very important because, for example, in the case of the renormalized mass, we know that the renormalized mass will be a function of the bare quantity. And so we will have this function. So there is a relationship between the bare quantities and the lattice spacing, and this will allow you to choose how to flow towards the continuum limit. Now, obviously, whenever you have a system and you discretize it, you will also introduce systematical errors, both because of the discretization that you're using and of the finite size effect, because you will effectively, if you simulate the system, you will have to deal with finite size effects. But in the end, you will see that in most cases, we will be able to control both these systematical errors of discretization and the errors of finite size. So at this point, I think that 1 hour has gone by. It is time to make a break. And obviously, if you have any question, I will be happy to answer. I don't know, Claudio, do we take a 5-minute break?
Yeah, we can take a 5-minute break. And if there are questions, it is a good moment. Okay, I think that we can resume.
Okay.
So Davide, please share again the screen.
Yes, so let me. Okay, can you see?
Yes, please, go ahead.
Okay, thank you, Claudio. So now we have, I have tried to explain the finest conceptual point, so the difference between the proper continuum limit and the naive continuum limit in the case of the scalar field, because the computations are simple and intuitive. But obviously, in quantum field theory, we know that there is a problem with scalar fields, there is the problem of triviality. So if you take a scalar field and you push the cutoff to infinity, you will see that it will become a non-interacting field. So, for example, in the standard model, the only scalar field, pseudo-scalar field that we have is, scalar field is the Higgs field. And the problem with the Higgs field is that it has a problem of naturalness. So at some point in the cutoff, it will appear either as a composite object or as another kind of excitations. That is to say that the most important next step that I will undertake is the discretization of fermionic fields. And as we will see, even in the simplest case, sorry, I am unable to speak and write at the same time. So in this case, we will see that already at the non-interacting level, there will be problems. And there will be trouble, and so we will have to find a way out of the trouble. But this way out of the trouble will bring more precision to the statement that I have done before about the breaking of symmetries when we discretize actions. So once again, it is a nice exercise to deform the contour integral of the Minkowski action to work out the Euclidean action of the Dirac field. And it is interesting because this action is called, has been reproduced on arms and other parts of the bodies of many people and is depicted as the love equation, but unfortunately it is always written in a wrong way. But one must note that the Euclidean action has a plus here, so I urge you to note this plus, and there is no I. Very well, so when we want to discretize this action, we just go to the same steps as in the scalar case. So we write this as a to the fourth, sum over the lattice sides. Then we will have defined a conjugate field on the lattice sides. Then we will have our gamma mu. Remember that in the Euclidean, gamma nu has an anticommutator that is equal to 2 times delta. And it is also true that the Euclidean gamma functions are Hermitian. And this time, there is a problem. Now, what do we put here? We can put either the backwards or the forwards derivative. But to the contrary to the scalar case, in this case, we have only one power of the discretized derivative. So I won't go through the details, but it turns out that if you choose one or the other, so the forward or the backward derivative, in the end, you will get a theory that is non-normalizable because you are violating parity and you will have problems sooner or later. So the choice that we make is to just put the mean between the forward and the backwards derivative. And then we have our m naught psi n. Very well, so now let us, as an exercise, we can compute the mean between this forward and backwards derivative. And the result, acting on a psi n, the result will be 1/2 times 1 over a. 1 over a comes both from the forward and from the backwards derivative, so I can factor it. And then I will have psi of n plus a mu minus psi of n plus psi of n minus psi of n minus a mu. And now the first difference with respect to the scalar field, these two terms cancel, and we are left with 1 over 2a of psi times n plus a mu minus psi of n minus a mu, closed parenthesis. So our Euclidean action of psi and psi bar will be a to the fourth, sum over the lattice sides, psi bar n. Then we have the sum over the directions. that was implicit in the Einstein convention here. And in the sum, let me factor this object. And in the sum, we will have, a gamma mu, and then we will have psi n plus a mu minus psi of n minus a mu. And then we will have 1/2 coming from here. And then we will have the mass term, m0 times psi bar n times psi bar. Very well. Now, exactly as we did with the scalar case, we can say that the Euclidean action is dimensionless in natural units. So we can work out the length dimension of these psi fields, and we immediately realize that the length dimension is -3/2. So our fields can be rescaled. Sorry, can be scaled actually. I'm just explicitating the length dimension. And so I can do with the mass. So this m0 will become m0 hat. And why do I do this? It is exactly as in the case of the scalar field, because I want to write this as a dimensionless object, where now the operator in the action will be this d, depending on n and m. Sorry, and m. If you explicitate the indices on the lattice, you find that this is sum over mu of gamma mu delta of n8 plus mu m plus, probably, no, there is a minus here, minus delta of n minus a mu m, and then plus m0 hat delta mn. Once again, let me stress that this m is just an index of the site on the lattice and not the mass. The mass is m0. Now, as a result of this discretization, we see that our generating function that I remember is an integral over Grassmann fields will be a sum over the sides of the lattice of the Grassmann field psi, then of the Grassmann field psi r, and then it will be e to the minus sum over nm psi bar hat n dnm psi hat m. And this, you immediately recognize that in the case of Grassmannian variables is simply proportional to the square root of the determinant. And this is nice, both because it is a recipe to compute numerically, it is a recipe to compute numerically this determinant, although we won't proceed in that path. And you see the difference with respect to the scalar case, where this was proportional to minus 1 over the determinant. Very well. And again, if you want to perform computation, you can use Wick's theorem to decompose correlation functions, but in the end, you will need to compute the propagator, that is, again, the inverse of the operator D. Very well, and this is related to the dimensionless propagator, so let me call this D hat, because it is dimensionless. And D hat will be related to the true dimensionful propagator with a factor of n that comes from the length scale of the fields. Now, again, this is a repetition of the case of the scalar field, this case, fermionic fields. We are dealing with fermionic fields. But again, we should compute the propagator, because as I said before, from the propagator, we can both compute the diagrams and also compute the one particle spectrum that is of interest to us. So once again, we would solve an equation like that, where now G, sorry, let me call it n to the -1 of M and L equal to delta N L. So by solving these, we would find, by using Fourier transformations, we would find the form of our propagator in Fourier space. Let me call this G again. And the computation is completely analogous to the computation in the scalar case. And it is a useful exercise to perform the calculation. And the solution, obviously, you can find it in Smith, Roth, and all the books on lattice field theory. And the solution is the following. And I beg you to see the difference between the scalar case. Keep into account that I have performed the usual manipulation of multiplying on the denominator and on the numerator times this object, m naught minus I sum over mu of gamma mu times sine of k mu a. And this is very, very useful. So note, first of all, the difference with respect to the scalar case. Here you don't have k mu a over 2. And this is very important, as we will shortly see, because if you take the case of m hat equal to 0, then g tilde of k is equal to minus sum over mu gamma mu sine of k mu a over, then I explicitate the sum. So this will be sine squared over k4a plus the sum on the space-like direction. I say space-like even though we are in Euclidean space, because conventionally I have chosen the 4 direction as my time direction, but we are completely symmetric. Okay, this is the sum over sine square of KEA. And so from here, you see something terrible happening. Namely, that these as poles for K mu equal to 0, but also to plus or minus pi over A. So this is terrible, because it means that when I take the limit of A that goes to 0, I won't have one single fermion with its good dispersion relation and normal behavior. I will have 2 to the 4th equals 16 fermions. So I started with one fermion, I discretized it, and the result in the naive continuum limit is 16 fermions. Now, this is a long-standing problem called Fermion doubling. So the morale, if I have to relate with what I said before, is that we don't know to what theory we flow before actually taking the limit. What we require is that the naive continuum limit is the theory we want. But in this case, for example, we proceeded in the most simple way, and we got to a theory that is different from the theory that we started. Now, you might complain, and you might say, look, yes, you're right, but you took a theory that is non-interacting. So if you add interactions, the problem will go away. Actually, this is a problem the problem of fermion doubling has been studied over the years, and it turns out that the doubling also happens for m naught different from 0. And this is because in the calculation I set m naught to 0. And one can explicitly compute the inverse Fourier transform of the time part of the propagator. Exactly as before, one gets a complex integral. You can solve this complex integral, and you find the dispersion relation, and you find exactly that the single fermions in the continuum limit go to 16 fermions. And obviously, and this also remains in the interacting case. The only difference is that you have poles displaced differently on complex plane. Now, this is not, I must stress it, this is not the only discretization that is possible for a fermion. We could have chosen to smear the fields on more lattice sites. We could have chosen to work in a larger number of dimensions and to have a dimensional reduction that is created at the statistical level that recreates our fermions in 4 dimensions. But the morale is that other discretization are possible. So one could ask whether there are general arguments to see when the doubling happens, and in general, what are the features that we might expect from the discretization of fermions. And actually, there is a theorem called Nielsen-Ninomiya theorem that says that if we have an action that is written in this way, so sum over the sides of the lattice of d n plus m psi, sorry, and here I forgot the variable. Now, if we have this kind of action, then we cannot have simultaneously the following. So the local operator, and this means that the inverse will be a periodic analytic function in Fourier space. So if this doesn't happen, I make an example. If you write down word identities, you will have derivatives of these propagators, and you will have singularities, unexpected singularities. So you better have a D local unless you want to correct for these difficulties. Then I have 2 conditions that go hand in hand. So the propagator at small lattice spacing goes like I times gamma mu p mu plus a correction, and then that dp is invertible for p different from 0. And this why are these why do these go hand in hand? Because these are the conditions that ensure that you have one single fermion in the night continuum limit. And then you have a final condition that is very important for simulations, the violation of chiral symmetry. So if this is 0, you have chiral symmetry enforced. If this is not 0, chiral symmetry is explicitly violated. So what does the Nielsen-Ninomiya theorem says? That you cannot have all these conditions realized simultaneously. Example, in the naive fermions that I have explained before, we are violating 2 and 3. But I can also formulate, as I said, I can smear the fermion fields, and I obtain the so-called staggered fermion formulation. But in that case, I violate 1. Finally, I can have Wilson fermions. I will do the calculation shortly. And in the case of the Wilson fermions, I violate condition 4. So I violate chiral symmetry explicitly. Now, in these two cases, so in the case of staggered fermions, I lose locality because the fermions are spread over more than one single fermion is spread over the neighboring sites. In the case of Wilson fermions, I will violate explicitly chiral symmetry. Let me stress that there are also other discretizations, but the sense of the Nielsen-Ninomiya theorem is putting conditions on what you can or cannot do. Very well, so let me go on to Wilson fermions. So I will try to just explain the logic. So basically what one does is that one adds a term to the fermion action depending on a constant r, and a term that is done like that. Psi bar hat, backwards derivative, forwards derivative, psi n. Now, what is the effect of this addition? We can work out the operator that is in the action. I put a superscript W to indicate that this is the Wilson action. And the result is to add a piece to the mass term. And this, look, you can see it from the use of this operator that was the same with respect to the scalar case. So we will have an additional term here with a delta and an m. Then we have a minus 1/2 sum over the directions, and we add also pieces to the kinetic term. And this is a calculation that you can perform. It is just a little bit lengthy, but nothing hard. Now you notice that you had expected to have chiral symmetry if m0 was equal to 0, but in this case, this is not true. This is not true because there is this factor r. However, if now you do the computation of the time dependence of the propagator at large Euclidean time, you are able to work out the dispersion relations, so to work out the mass as a function of the momentum, and you note that this is equal to the following. So this is over I. So you realize that when pi is equal to 0, the limit of this object is simply m. Sorry. But when pi is equal to pi over a, this limit will rather be equal to plus infinity. So what you have achieved here is the decoupling of the doublers. The doublers will go to infinite mass, and as a result, they will not bother us in the continuum limit. I have taken the case before of this m0 hat equal to 0, but you can perform the computation. It is reported in the book. It is reported in the book by Ian Smith, and again, it is a simple complex integral, and you find this result. So we have found a way to solve for the problem of doublers. However, we have broken chiral symmetry explicitly. What does this mean? It means that if we want to recover chiral symmetry at the end of a calculation, we will have to find a renormalized quantity that enforces chiral symmetry and realize it in the continuum limit. But we won't be able to compute things that are chirally symmetric in a discretized way. For that, we will have either to accept the doublers or eliminate them in some other way, or to choose another discretization, for example, the staggered discretization. Okay, so at this point, are there questions? Okay, so I guess not. I can go on to gauge invariance. So we have dealt with scalar fields. We have dealt with fermion fields. Now it is the time to pass on to gauge fields. So the best way to introduce this is to simply write down the action in Euclidean space for a fermion interacting with gauge field. Where I introduce this G naught. So G naught will be the coupling constant that is hidden into the covariant derivative. And inside A mu, I've chosen to use A mu that has inside of it the coupling. So the coupling appears in the second term of the Lagrangian. And the thing to note here is that these J naught and M naught will be bare quantities, so that they are when we discretize, they will be defined at the scale of the Rao cutoff. But the most important property of this action is that if I do a transformation on this psi field that are vectors in some representations of a Lie group large G, and these can be SUN, but it can also be SP2N, the symplectic group, or SON. Or, and look at this, you can define the gauge, the gauge Ising model. So you can have whatever you want. And this transforms with the conjugate representation. And all this covariant derivative affair is defined so that the covariant derivative transforms covariantly, as the name says, with the transformation of the gauge group. Now this is called the gauge transformation, and the action here, SE, is invariant with respect to this. And this is well known. Now I can write omega x as the exponential of a function of x times TA, where TA belongs to the algebra that I write in, let's say, algebra of the group G. And so we have the following conventions that will be useful in the following. We can always choose these to be normalized like that. And then our F mu nu will be simply the commutator between the fields, otherwise written this. So sorry if I go this long in defining the objects, but at least we have fixed some notation. Now, the important part of this is how to discretize this kind of action. Now you remember that there is a tight relationship between gauge invariance, the principle of gauge invariance, and the concept of parallel transport. So basically gauge invariance states that the field psi belongs, is a vector that in the space of the algebra of G, and it transforms according to a particular representation of G. And at each point, you will have a different basis. So the statement of gauge invariance is that the results, the things should not depend on the choice of basis. Now this can be made true by using parallel transport. So say we have to compare psi x with psi y. then we cannot on the outset compare them because they are defined at different points that have different bases. And so we have to define, let's say, along a path that goes from x to y, a path that I will call CXY. We have we cannot compare psi x and psi y. We have to compare psi y with U parallel transporter psi x. So this is called parallel transporter. So if I define V with the subscript, the space in which psi lives, this lives in psi x, all this object lives in Vy. So we are good. Now, I won't do the calculation, but it is possible to define an equation, a differential equation for the parallel transporters. I just will state the result. These parallel transporters take the form of a path-ordered exponential of I times the integral over the path of a mu, the x mu. And these objects have many interesting properties. For example, if the path is identical, it means it doesn't move, then we have the unit matrix. If we have two concatenated paths, then the parallel transporter is just the product of the parallel transporters on the path. And if I invert the sense of motion along a path, then the parallel transporter will be the inverse. Now, in the cases in which we deal with a unitary group, this will simply be the adjoint. Important fact, if you look at the gauge transformation properties of this object, you realize that it will transform like that. And this is important because if you want to define gauge invariant and gauge covariant object, now you just have to follow the rules of gauge transformations. And so, for example, you can define objects that are gauge invariant. For example, psi bar y u going from x to y psi x. These I will also denote in this way. And then you can define important objects called Wilson loops. Trace, and I will explain why. So parallel transporter along a path gamma, a closed path this time. This, by definition, is the exponential of I going in a closed path of a mu, the x mu. Now, why do I put the trace? If you put the trace around this object, you immediately realize that from the cyclic property of the trace, these objects will simplify because being a closed path, y and x will be equal. So this is an invariant object. But we can also define covariant objects, and it is obvious that, for example, the discretized derivative, sorry, actually, the derivative can be written as, sorry, not h bar, this is confusing, parenthesis of now the parallel transporter from x plus h to x minus psi x. And this is a clear way to tell us how to discretize these objects. This can be easily discretized. We simply have to consider as elementary path of our system the links of the lattices. So if we have a link between n and n plus a mu, we just define the parallel, mu, the parallel transporter starting from n and going in the positive direction, mu. And I ask you to pardon me because these are inverted. So you always start from the second argument of u and go backwards. And this is defined as the exponential of I integral from n plus a mu of a alpha, the x alpha. So with this definition, you see that this is basically the mean value of the gauge field over a link. With this definition, you see that the gauge invariant object is no more psi plus n, psi of n plus a mu minus psi of n minus a mu, but rather u mu psi of n plus a mu minus psi dagger n of psi minus a mu. Okay? And we don't use that. And then let me just write the Wilson action. When we add a gauge field, we can go over exactly the same steps as I did now twice for the scalar field, and I just told you how to go about it for the Fermion field. But this time, the gauge matrices will appear. Let me stress that these matrices are elements of the group. And this is a difference with respect to the continuum case where you have elements of the algebra roaming around. And the difference is that, as I said before, in this case, you can also use discrete gauge groups. And this has been historically very important because it has allowed to perform large numerical simulations at a moderate computational cost. Very well, so now we have this discretization. If we plug it, for example, into the generating function, we have something like that. So I will use this to indicate, as always, the discretized functional derivative. And now we will have an integral over u of the Wilson action and of the discretization of the Young-Mills action that we will now see. Okay, so the gauge part by itself is interesting. As you all know, the pure gauge systems are interesting by themselves. States are predicted to be present in the spectrum of these actions, states called blue balls, that so far have escaped any detection, but there are clues as to the mass where they should be detected, and they, for example, they should appear as supernumerary states, and they would be the definitive proof of the correctness of QCD, should one need other proofs that are outside of the perturbative regime. Now, one could ask, what is the gauge action? We have dealt with parallel transporters. Now, the simplest object that you can build with this parallel transporter that is at the same time non-trivial and gauge invariant is the gauge transporter around a closed path, a closed plaquette on the lattice, and the name here, the P means plaquette. Now, if you go around this plaquette, this is also denoted as U, mu, nu, n, because n, mu, and nu are the only informations that are necessary to identify the plaquette on the lattice. And you see that you have to start with U, mu from here. Then you have to multiply with U going in direction nu calculated in n plus a mu, so here. And then you would have to start from n and go in direction minus mu, and this you can do by simply putting a dagger. Let me remind you that this is written like that. And then last step, I have to go backwards in direction nu, and an object that is computed starts from a n plus a nu. Very well. Now, with this object, that is the simplest one can define on the lattice, I can define the so-called Wilson action. So the name is the same as for the Fermion action, but if one speaks about gauge actions, it is commonly believed, it is commonly used as a name for this action, and it has this strange definition that now I will explain. So there is a sum over the sides, there is a sum over the pairs of directions with the condition that they never coincide, and one is larger than the other. Keep in mind that I could have written the same as follows. So the 1/2 comes from the sum over directions. Very well. And we have 1 over 2n because we will need to normalize the traces of this object. Now, what happens if I try to take the naive continuum limit of this object? I have to define, I will define this object like that, and for ease of computation, I will just call it b mu. And you see that the b mu will appear in all these pieces, so it will be a product of exponentials of b mu. But in this case, remember that we don't have exponentials of objects that commute. When you have a product, you have to use the BCS formula. Basically, you will have an additional piece. But if you write explicitly these objects by using the Taylor expansion at first order, even if we are in discrete space, we can think of discrete space as some specific points of continuum space. This can be written in this way, for example. This, for example, that appears in the Hermitian conjugate will be minus b mu n plus nu, and you can verify these by looking at this drawing. And this, again, using the Taylor expansion, will be done like that. Finally, okay. So now, if I write explicitly this u mu nu, by using the Taylor expansion, I will have a product. Sorry. A product of exponentials. And I won't do the calculation, but it is very instructive to do it. So I won't write all the object. Because using the BCS formula, one is able to demonstrate that this is equal to the exponential of I a squared f mu nu, with f mu nu equal to f mu nu a ta, with a sum over a. Now, why is this important? This is important because in the naive continuum limit, we can expand this object, and it will be at first order. Sorry, let me have a look. At first order, a squared f mu nu. At second order, minus a to the fourth f mu nu squared. And this is very important because if now you expand the Wilson action so let me write it correctly, mu larger than nu, you will have a 1, then you will have 1 over 2n real part of the trace of 1 plus a squared f mu nu minus a to the fourth 1/2. Sorry, here I made a mistake. There is a 1/2 here. F mu nu squared plus terms of higher order. Now note that this choice of 2n was made to have these two terms contributing with a 0. Here I have the real part of the trace, but the trace of algebra matrices is simply 0. So this is 0. And so the result is beta. I have a minus coming from here and a minus coming from here. So I have beta times a to the fourth. Then I have 1/2 coming from here. Then I must remember that I had normalized the algebra in this way. So in this squared, I will have another half. And then I will define the sum to go on the sides of the lattice and on all the directions. So I will have an additional 1/2. And at the end, I will have a trace over f mu nu, f mu nu. So this, I require that this tends to the Fermion action that I had defined at the beginning. Sorry, not the Fermion action. What am I saying? The gauge part of the gauge invariant action. And this happens if and only if beta times 8n, sorry, here I forgot the n, is equal to 1 over 4 times g naught squared. So in this case, we are able to compute explicitly the relationship between the beta and the bare coupling. That is the coupling computed at the scale of the lattice spacing. Note that in writing the generating function, this time we just have an integral over the group. And let me stress that this integral is now an integral defined on each link of the lattice, where this is the R invariant measure that has the property it is the unique measure to have the property of being invariant under the action, the left and right action of the group. So basically, the path integral becomes a finite multidimensional integral if the group is compact. Otherwise, I think that the R measure is not unique anymore. And then, most importantly, we have no need for gauge fixing, because the integrals are not over infinite gauge equivalent replicas, but just over the orbits of the gauge group. Very well, so I am almost at the end. What we have done is to discretize we have discretized many different actions. So we have come to the conclusion that if we have, for example, if we have a system of gauge fields and fermions, the object that we will have to compute is the following. I don't know why I choose to use the bold. Okay. And then the sum of the Wilson-Dirac action and of the Young-Mills action. And this is the object that is normally computed in Monte Carlo simulations. That will be the subject of lecture 2. Now, let me go back to unbold. In general, we could go towards lattice QCD as a discretization of QCD. So with more than one species of fermions, we can add all the specificities of QCD. We could also use particular boundary conditions to add QED. As you know, there are differences, namely there is no asymptotic freedom, and also there is a problem in the conservation of charge at the lattice level. This you can find in the modern literature. But in general, the lattice regularization of QCD will be a non-perturbative, the only first principle non-perturbative regularization of QCD. So it will allow us to explore the non-perturbative regime, and by that I mean the regimes where the coupling is large, and for example where you have confinement or chiral symmetry breaking, by running simulations on a computer. Let me anticipate what I will explain in the next lecture. By performing computer simulations, we will not compute from the outset the real system. We will introduce systematical errors of discretization. So we will have to break some symmetries, and we will have to check that these symmetries are re-established after we have renormalized the theory. And we will also have to check for finite volume effect. But this will have to be sent to 0 by hand. And I will reveal to you what this obscure way of saying means in the next lectures. Very well. So if there are some questions, I'm glad to answer.
So thank you, Davide, for this nice introduction to the basics of lattice field theory. So if there are questions, please don't be shy and ask. Just unmute yourself.
Hi. So can you hear me?
Yes.
So mine is probably just a curiosity rather than a question. Everything was very clear. So thank you for this first.
Thank you.
So when you said when we have to deal with QED, we have to take care of the boundary conditions. Could you just elaborate a little bit on that?
Yes. So I must you catch me unprepared, but because I do not know the details of the lattice regularization of QED. But what I can tell you heuristically is that if you have QED, then with boundary conditions and you have a positive charge, you have a problem, because this charge will radiate, and with boundary conditions this is not possible because the field will come back. Okay. This is strange.
Yeah, okay. So, that makes sense.
So the trick is called C* boundary conditions. So the trick is the following. Imagine you have a plus charge, and let me represent a replica of the system. Here you have C* boundary conditions. So the continued here will have a negative charge. So no problem. Does that answer your question?
Yes, thanks.
Thank you.
Thank you.
So I will do a shameless marketing, but look for papers by Agostino Patella, Biagio Lucini, and others about C* boundary conditions, and you will find the answers. I am sorry, I am neglecting many authors, but I know that Agostino has been working on that. So it is the first reference that comes to my mind.
Perfect. Thanks.
Cheers.
Okay, are there any questions? Any other questions? So if not, let's thank again Davide for this nice lecture. And I just recall that tomorrow there will be the next and final lecture about Lattice QCD by Davide. So thank you all for being here, and see you tomorrow.
Thank you. See you tomorrow.